This tiny recursion tree is asking the same question again and again, like a person rereading the same page because they never wrote the answer down. Dynamic programming starts when repeated questions become expensive enough that remembering is no longer optional. Psychologically, this is the human habit of rethinking the same worry from scratch instead of writing down the answer. By the end, you should be able to spot repeated subproblems, watch a recursion tree collapse into a memo table, name the state being saved, and fill a table only after its smaller answers exist. Naive Fibonacci recursion branches into many repeated calls. The same fib of 5, fib of 4, and fib of 3 appear again and again. The useful dependency question is which earlier answers this cell is allowed to read before it writes its own value. That direction turns a table from random boxes into a proof. A state is a precise smaller question. If the state is vague, the table becomes vague. Good DP starts by naming exactly what answer is stored. The state DP, I, C, means the best value after considering item I with capacity C. The key beginner mistake is thinking DP means a table. It does not. DP means the problem naturally asks repeated, reusable questions. The table is just one way to remember those answers once the questions are named clearly. Memoization keeps the recursive shape but adds memory. The first time a state is solved, store it. The next time, reuse the saved answer. The second call arrives at an already filled memo cell and returns immediately. Tabulation flips the direction. Instead of waiting for recursion to ask, fill smaller answers first so larger answers can read them safely. Sweep the table from base row upward so no cell reads the future. Pause before filling the cell. What exactly should this table remember? Watch a tiny trace. Fib 5 asks Fib 4 and Fib 3. Fib 4 asks Fib 3 again. The repeated Fib 3 is the waste. Once that answer is saved, both branches point to the same cell instead of rebuilding the same subtree. The real test is whether the table remembers a named question, not whether it merely fills space. A DP table is not just a grid. Arrows show which cells depend on which earlier cells. Fill the table against the arrows and the logic breaks. The useful dependency question is which earlier answers this cell is allowed to read before it writes its own value. That direction turns a table from random boxes into a proof. DP works when the best answer to a big problem can be built from best answers to smaller problems. That property is called optimal substructure. Memoization and tabulation solve the same memory problem from opposite directions. Memoization starts with the original question and saves whatever recursion asks. Tabulation starts from known small answers and deliberately builds upward. The other ingredient is overlap. If subproblems never repeat, storing them may add memory without saving much time. If they do repeat, every duplicate branch is pain until memory turns it into one saved cell. A recurrence says how one state is computed from other states. In DP, the recurrence is the recipe the table will execute. For Knapsack, one explicit recurrence is, DP at item I and capacity C equals the better of skipping the item or taking it if it fits. A state must include every detail that can change the answer. If capacity matters, capacity belongs in the state. If position matters, position belongs in the state. Missing one detail makes two different problems share one misleading cell. Base cases are the cells whose answers are known immediately. They are not decorative starting boxes, they are the anchors that make every later cell meaningful. The useful dependency question is which earlier answers this cell is allowed to read before it writes its own value. That direction turns a table from random boxes into a proof. Before the recurrence writes anything, identify the base cells that make it legal. The real test is whether the table remembers a named question, not whether it merely fills space. Many DP problems ask, choose this option or skip it. Take this character or move past it. The table records the best result after considering those choices. In Knapsack, a state can mean, using the first I items with capacity C, what value can I achieve? The row and column names carry the meaning. A single cell means, using the first I items and capacity C, what is the best value we can carry. In edit distance, a state can mean, how many operations transform this prefix into that prefix. Neighbor cells represent insert, delete, and replace choices. In Knapsack, do not read the table as spreadsheet decoration. Each row means how many items are allowed, and each column means remaining capacity. A single cell asks, with these items and this much space, what is the best value I can guarantee? Some shortest path problems can be seen as DP over an order of dependencies. The bigger idea is the same, solve predecessors before successors. Nuance, shortest paths become DP when dependencies have a usable order, such as DAG shortest paths, or when repeated relaxation simulates that structure. Memoization and tabulation are not different religions. They are two ways to organize the same dependency graph of subproblems. Before filling the next square, trace the arrows backward and name the smaller questions it needs. The real test is whether the table remembers a named question, not whether it merely fills space. If a row only depends on the previous row, you may not need the whole table. Space optimization is safe only when the discarded cells will never be needed again. A rolling buffer keeps only the rows the next computation still needs, so old rows can safely disappear. A wrong state loses information. If two situations need different futures but share one table cell, the DP will mix them and produce confident nonsense. A good state preserves every fact the future needs. If two different futures share one cell, the table will lie confidently. Many DP bugs are not math bugs, they are naming bugs, where two different situations get forced into one cell. A correct recurrence can still fail if cells are filled before their dependencies exist. Order is not an implementation detail, it is part of the proof. The useful dependency question is which earlier answers this cell is allowed to read before it writes its own value. That direction turns a table from random boxes into a proof. Tabulation is safest when the arrows all point from already filled cells to the current cell. If an arrow points forward into a blank space, the recurrence may be correct, but the fill order is wrong. The formula can be beautiful and still betray you if it reads a future answer that does not exist yet. DP buys time by spending memory. If the number of states is enormous, the table may be too expensive even when the recurrence is correct. The mental move is compression. A recursion tree repeats nodes, a DP table merges identical states into one stored answer. Make the collapse explicit, two identical recursion branches should visibly become one shared memo cell, not two separate boxes. Here is the bug checkpoint, do two different futures accidentally share one state? The real test is whether the table remembers a named question, not whether it merely fills space. Every arrow in the transition diagram says, this answer can help compute that answer. The table is just a systematic way to walk those arrows. The usual DP cost is number of states times work per state. That receipt is often clearer than trying to guess big O from code after the fact. The useful dependency question is which earlier answers this cell is allowed to read before it writes its own value. That direction turns a table from random boxes into a proof. A useful DP estimate is number of states times work per state. That is why naming the state is not just math notation, it tells you the memory cost and the running time. Ask, what is the state, what are the choices, what are the base cases, what order respects dependencies, and how many states exist. Pick one target cell. Point to the earlier cells it needs. Read their values, apply the recurrence, write the answer, and never recompute that state again. Work one tiny cell slowly, read the skip value, read the take value, choose the better one, then write that number so future cells can reuse it. The final habit is to say the state in plain English before writing a formula. If you cannot explain what one cell means, the recurrence will look official but the table will not actually teach or debug the problem. The real test is whether the table remembers a named question, not whether it merely fills space. Dynamic programming is memory with a job. It remembers repeated subproblem answers so the algorithm can move through a dependency map once instead of wandering through it repeatedly. Predict the next value from the neighbor cells before the table reveals it. The real test is whether the table remembers a named question, not whether it merely fills space. DP needs overlapping subproblems and optimal substructure. Memoization saves on demand. Tabulation fills in order. The state definition is the soul of the solution. Next, we will study greedy algorithms, where the challenge is proving that a local choice is